Hey everyone. Today we're going to learn about how Java stores your stuff in memory. All right, guys, stop arguing. Stop arguing. Thank you. So, Java keeps most of the things that you store in variables and fields and elsewhere in two different places. One is called the stack and one is called the heap. The heap stores all the objects. And I mean all the objects, with no exceptions, including arrays. And just for reference, it also stores all your class variables. In other words, those that are declared static. Then the other piece of memory, the one that we're really going to learn a lot about today, is called the stack. The stack stores all of the local variables, including parameters. And the stack is what makes it possible for one method to call another method, and the stack is what makes recursion possible. So we're going to talk about how your variables are stored when you do things like recursion. First of all, when a method is called, Java creates a stack frame for that method. Stack frames also have a fancier name. Some people like to call them activation records. I guess because stack frame doesn't have enough syllables and make them feel big enough. So what is a stack frame for? Its job is to store all the parameters and local variables for that method call. Now, of course, one method can call another method, which can call another method, and so on. And for that reason, the JVM maintains an entire stack of stack frames. And that's why they're called stack frames. And so you can think of this stack as just being a bunch of dishes, like plates, piled one on top of the other in a stack. And that way, you can go as high as you want. You can call method after method after method if you like. So I'm going to show you a snapshot of what a stack looks like when Java is executing some methods from the insertEnd class. And I'm going to, just like a stack, I'm going to work from the bottom up. So you might want to leave a little space on your paper. And I'm going to divide the board into two sides. And everything on the left is going to be the stack. And everything on the right is going to be the heap. So, generally the first thing Java does is it calls some method called main. So let's suppose that there's a main method in slist whose job is maybe to test your slist class. And main always has a parameter. The parameter, we usually call it args, though you can name it whatever you like. And args generally points to, as we've learned, an array of whatever words were typed on the command line represented as string objects. Now, strings are objects, arrays are objects. All objects are always on the heap. They're never on the stack. So that's why I've drawn the array and the strings that it points to on the heap. Now, maybe slist has some local variables as well. Like, if we're going to test an slist class, we should probably make a list. So let's have a variable called list. And maybe at this moment, it points to an slist that's currently empty. So the head is set to null, and the size is set to 0. But we want to test the slist class, so maybe the main method has some object, let's just say it's a string, that we want to add to the list. And the string might be something from your shopping list, like milk. Okay? So main is ready to insert that string into that list, and so it calls the insertEnd method to do that. When it does that, Java, the Java virtual machine, creates a new stack frame on the stack for the insertEnd method and piles it on top of the stack frame for slist.main. Now, slist.insertEnd has some parameters of its own. First of all, it has a parameter called this, which points to the actual slist that we called insertEnd on. So this is kind of a hidden implicit parameter. There's also an explicit parameter. We pass to insertEnd the object that we want to insert at the end of the list. And if you recall in the insertEnd code, I think we called that obj. And so str gets passed as a parameter to obj, or it gets copied as a parameter for insertEnd. Question? No, this is a local variable. This is always a local variable. It is not kept inside an object. It points to an object, but it's kind of the starting point for a method to find the object that it's operating on the stack.
So it's just in all methods?
Any method that's not static. Right. Any method that's not static has a this variable, and this variable is always kept in its stack frame. So thises are never on the stack. They're always in the stack frames. And while we're on the subject, main does not have a this method because main is a static method. Or sorry, main does not have a this field because main is a static method. So now insertEnd is ready to insert this object milk into this list. And so to do that, it needs to create a new slist node that we can add to the slist and use to point to this new object. So we're going to add another stack frame up here, which is the slist node constructor, which I will just call slistnode.slistnode. And the constructor takes a parameter, which is the thing that we want to store in the slist node. And it also actually constructs a brand new slist node, which this points to. And the slist node has an item field and an next field. And the obj field is a parameter which got passed in by insertEnd. InsertEnd passes in obj as a parameter, so that parameter gets copied. And that's what that looks like. And then we could go on executing from there. The next thing that would happen is that the slist node constructor would copy this value into the item field. So now our slist node actually points to an item. And then it would terminate, but I'm not going to go there. I think that's everything. So again, this is the stack. I put the method names on the left. I put the parameters, including local variables, local variables including parameters on the right. And everything that's not on the stack meaning all the objects is the heap. Any questions about this? In the back here. Mm-hmm. Mm-hmm. Well, when a method ends, the stack frame for that method is deleted, blown off the stack. So in fact, that's what I'm going to talk about next. It's not garbage collected. So garbage collection is something, well, you don't really need to worry about it yet. We'll talk about it later in the semester. But garbage collection is something that happens to objects on the heap only. Garbage collection really doesn't have anything to do with the stack. The way that stack frames get vaporized is when a method ends, the frame is vaporized right then and there. No waiting for garbage collection, it just happens. Other questions? Okay, so as I just said, when a method finishes, its stack frame is erased. Permanently and irrevocably, and all the variables that were stored in that stack frame just disappear. And now that doesn't mean the objects that they point to necessarily disappear, but if there's an object that only one stack frame points to and that stack frame goes away, then there's no way to reach that object anymore. And it will eventually be garbage collected. Now, at any given point in time, the method on the top of the stack is always the one that is currently executing. All of these other methods down below it on the stack, they are waiting for the methods above them to finish executing so that they can resume again. One thing that's sometimes useful for debugging is that in the Java-Lang library, the one that's automatically included, there is a method called thread.dumpStack, meaning it's a static method in the thread class. You just call it like that, thread.dumpStack. And when you do, what it does is it prints a list of all of the stack frames that are on the stack at that moment. So if you're wondering, how on earth did my slist_node constructor get called, then you can always call thread.dumpStack from inside the constructor, and it'll print out a list of all of the methods in order that were on the stack, so you can see how it got called and how we got there. Question?
So thread.dumpStack is a system.
Well, I've never actually looked at the thread.dumpStack code, so I'm not sure if it uses system.out.println, but it does print to the screen. Yeah, it prints basically to the standard out is what it's called. Yeah. Java.lang. So that's the one that you don't have to import. Other questions? Maybe I'll write that down. So the stuff I've just showed you is a prelude to parameter passing. Because it's important to understand how parameters are passed in Java and what happens to parameters when you change them. So parameter passing in Java is like in Scheme. All parameters are passed by value. Which is a fancy way of saying that the parameters are copied. And the copies are not the same as the originals. And that means that the method that receives the parameters cannot change the originals. But there are some subtleties there, so we're going to go over that. So, this is where the code that I handed out to you comes in. So I'm going to put that up here. So what I want to do here is play with calling some of these methods in this class called intBox and see what happens. So let's start with this static method called doNothing. I want to see what happens when I call it from another piece of code that's maybe somewhere else in this class, maybe in another class, but it's in a different method somewhere. And the code looks like this. First, I'm going to declare a variable int a equals 1. And then I'm going to call doNothing on a. And we want to see what happens when I do that call on the stack. So what's going on is that this code here is in some method that has a stack frame. And in that stack frame, there is a variable called a. And this code sets that value to 1. And then it calls this method doNothing. And when we call that method, we throw a new stack frame on the stack for the method doNothing. And the parameter called x gets passed by value, which means that there's a box in doNothing's frame called x, and we make a copy of that number 1. What happens next? Well, we execute the code in the doNothing method, and that sets x equal to 2. But, and the important thing is, when x changed to 2, a did not change. A is still 1. So now the doNothing method terminates, and when it terminates, its stack frame is erased. It's no longer on the stack. So the doNothing method, true to its name, did nothing of consequence here. It tried to change the value of a and failed, because that's how pass-by value works. So what if you want to be able to make a change in a method that you call and have that change appear so that the calling methods can see the change? This is an example of how to do that. This next method called set3. So here's the thing. In this case, the parameter is not an int. The parameter is a reference. And when a parameter is a reference, then the reference gets copied, but not the thing it points to. Well, the object it points to. So you can still change whatever's inside the object, even though you can't exactly change the reference. So here's another example of code. I'm going to say intBox b equals new intBox, and create a new intBox object. And then I'm going to call the set3 method on that intBox. And let's watch on the stack what happens. First of all, in the local method, whatever it is, I have a reference called b, and I create an intBox object on the heap. And this line makes b point to that intBox object. The intBox has inside it a variable called I. Now we call the set3 method. And the set3 method, which we call in the intBox, takes this parameter IB, which you recall from right here, And that parameter IB is a copy of B, because we always pass references by value, which means we make a copy of the reference. So now we have two references pointing to the same object. So the next thing that intbox does is it sets IB.I equal to 3. So we follow the IB pointer, we find the intbox, there's the variable I, and we set it to 3. And now the set3 method is done, and it terminates, and its stack frame goes away, but its influence does not go away because we've actually changed the object. The object now has the number 3 in it, and B still points to that object. So that is a way that, if you want, you can pass a whole bunch of information from a routine that you call back to the routine that calls it. Now, my last example here, this bad set 4, is an example of how not to do this. So, an example of how you might have a bug when you're trying to do what I just showed you, but you fail. And here's how this example works. Suppose, again, that we've just executed this code here, and now I execute bad set 4. What happens? Well, we create a new stack on the stack, a new stack frame on the stack for bad set 4. And bad set 4, just like set 3, has this parameter called intbox, or called IB, which points to the object, except it doesn't point to the object because we did something different. The first thing we do is we change IB by creating a new intbox. So IB did point here, but the first line of code changes IB by creating a brand new intbox that contains a 4. And now IB points to that box instead. Well, but the original intbox didn't change, so when this method terminates, the bad set 4 stack frame goes away. Now we have two objects on the stack. The one that has a 4 in it is inaccessible, so we didn't succeed in doing anything. And the old intbox still has a 3, so we tried to change it and failed because we didn't know what we were doing. And this is a common programming error, which is why I bring it up. Any questions about any of this? Yes?
What if the parameter was primitive? You couldn't change the value the same way you did?
What if the parameter was what?
Where you have int plus ID.
Uh-huh.
What if you had like int x?
So that was the original example, I think, the original example was where you have int x as the parameter instead of an object. What's that?
So you can only change an object, not a parameter.
If you want to pass information back from the called routine to a calling routine, other than the return value, you generally have to do it through an object, yes. So, and that's the standard way of doing it here. For those of you who have ever studied a language that has something called pass-by reference instead of pass-by value, this business here, set 3, is about as close to pass-by reference as you can get in Java. So now I want to take a look at how this applies to a recursive method. So we're going to look at an algorithm for doing something called binary search. Sort of one of the first simplest algorithms we'll look at this semester of any complexity. And the idea of binary search is that we want to search a sorted array. So someone's given us an array that's already sorted, like the phone book, and we want to search it for a particular name. And so, for instance, for our example here, we won't use the phone book. We'll just use an array of ints because it's nice and simple. And suppose we have just a simple array of ints, and we want to search it for a value that I will call find me in the code. And what I want my binary search to do is, if we find me, then we want to return its array index so that we know where it is in the array. And if we don't find me, then we just return failure. Failure is going to be a predefined constant with some special value, which is why I'm writing it in all caps. How do you do binary search efficiently? Well, the obvious way to do a search through a list is just walk through the whole list and until you find the item that you want. If you tried doing that with the quickly learn that that's no fun. So we want something faster than walking through the list. So when you look for a name in a phone book, well, you probably do it by kind of a subdivision technique where maybe you open the phone book to the middle, you see if you're too high, too low. If you're too high, you go halfway to the left. If you're too low, you go halfway to the right, and so on. That's what we're going to do in binary search. So suppose I have an array like this. And suppose we're searching for the number 1. So how am I going to search for it? Well, the first thing I'm going to do is I'm going to take the middle element of the array, and I'm going to look at that one first. And see, is that equal to 1? Is it greater than 1? Or is it less than 1? Well, it's less than 1, so I know that the thing I'm looking for has to be to the right. So that basically cuts the number of choices in half. And so the second thing I'm going to check is the middle element of what's left over. Is that bigger than 1, less than 1, or equal to 1? Well, it's bigger than 1, so I need to go to the left. And well, I've narrowed things down pretty fast, so again, I check the middle element of whatever's left over, and bang, I have a hit. I have found my 1. Any questions about that? Yes? If the array length is even, then you have to pick one that's a little bit off center. But it's not a big deal. Because even in that case, you're going to eliminate at least half of the elements, even if it's an even number array. Other questions? All right. So I'm going to do this recursively. My recursion is going to have 2 base cases. Maybe it won't have any base cases. So one base case of the recursion, obviously, is if we find the thing we're looking for, we can stop. So in other words, if find me is equal to the middle element of the array or the subarray that we're looking at, then we just return its index. And we can stop right away. Don't have to keep searching. The second possibility is that we will keep chopping our array in half and chopping our array in half and so on until we whittle it down to 0. And that's the second base case. If you have a subarray of length 0, there's nothing left to search. And in that case, we return failure. So those 2 base cases are pretty easy, and filling in the rest of the code is a little more work, but let's do it. And again, this is on the piece of paper that I handed out. So you've got it in front of you. So you can see at the top I've set failure is a constant. It's final. And I've set it equal to -1 because no array index can ever be -1. So it seems pretty suitable. Now, there's actually two binary search routines. There's going to be the main one that you call from when you want to search a whole array, but there's also another one up here that's for subarrays that does the recursion for us, because we need to be able to search just part of an array by binary search. So what we pass into the bsearch method is the array we want to search, the leftmost and rightmost index we want to consider. So maybe I'm saying only search indexes 3 through 7 of this subarray, and the thing that we're trying to find. And I start off, this code here is to handle base case 2. Because if the left index is bigger than the right index, that means we've whittled the subarray down to size 0. There's nothing left, and we can stop. Otherwise, there's still some array left to search. So in that case, we just find the middle index, which is halfway between the left and the right index. And since this is integer division, if we have an even number of elements in the array, it'll just round off the 0.5, but we'll be close to the middle. Then we check to see if we have actually found the correct element that we want. So if find me is equal to the middle element, that's base case 1, and we're done. But otherwise, we have not found what we're looking for yet. So we either have to search the subarray to the left, or we have to search the subarray to the right. So if the thing we're looking for is less than the middle element, then we search the subarray to the left, which means all the indices from left to mid -1. On the other hand, if we need to go to the right, then we search all the indices from mid +1 to right recursively. Are there any questions on this? Yes? Well, the left and right mean I want to search a subset of the array from index left to index right. So if left is 3 and right is 6, I want to search all the elements from 3 to 6. If left is 3 and right is 3, that means there's only one element left to search, 3. And then the next step after that, left will be 5 and right will be 3, or something like that. And then we're really done. So a very important question is, how long does binary search take? How fast does it run? Well, suppose the array starts with n elements. In one call to bsearch, before we do with recursion, we eliminate at least half of the elements from consideration. So after the first round, we've only got n over 2 elements left. And then after 2 checks, we've only got n over 4 elements left. So you can see we start with n things to check, then we've got at most n over 2, then we've got at most n over 4, then we've got at most n over 8, and so on. How many times does bsearch have to call itself before this number gets down to 1 or less? And the answer to that is the logarithm, the base 2 logarithm of n. And so this runs pretty fast. Instead of taking time proportional to the number of items, it takes time proportional to the logarithm of the number of items. So if you've got 1 billion items, Well, the log base 2 of that is about 30. 30 checks is a lot less than a billion checks. And if you're not familiar with logarithms, then you really, really need to know logarithms to get through this course and to be a computer scientist. They're just everywhere in computer science. So if you don't feel totally comfortable with reasoning about logarithms and doing equations on logarithms, there's a review in Goodrich and Tomassia of that. So I recommend you read sections 4.12, which is the logarithm section, and also 4.17, which is the exponential section and is closely related. All right, so now I want to draw the stack while this thing is executing so that you can see a recursive method and how it looks on the stack. So we start with the main method. Is the first stack frame. And it has some args, but I don't care about those now, so I don't know. This points at something. I'm not worried about what. Then suppose it makes a call to bsearch with an array This is the bottom bsearch. This is the bsearch with 2 parameters at the bottom of the page. And presumably main has passed it some sort of array to search through. And that array, we're going to use the same one that's over there. So I want to search through that array, and I want to find the number 1. Now, that method is going to call the other bsearch, the one with 4 parameters, in order to get things started. So we've got the other bsearch, the 4-parameter bsearch, on the stack with the same I and the same find me. And with left set to 0 and right set to 6, because at this point we're searching the whole array. And so what bsearch is going to do is it's going to compute what the middle element is. So middle element halfway between 0 and 6 is 3. And it's going to check element number 3. Sees it's a 0. 0 is less than 1. So we need to do a recursion to the right. So on with the next stack frame. Same value of I. Same value of find me. Time to go up to the next board. This is the same stack frame. And so now left is equal to 4. Why is left equal to 4? Because on the previous call, we decided mid was 3, and we discovered that the thing we're searching for is to the right of there, so it has to be at somewhere after 3. So it's somewhere between 4 and 6. And so we compute mid again. And mid is halfway between left and right, so mid is 5. And now we do one more recursive call. Once again, we have I, which points to the same array. Find me is still equal to 1. Left is still 4. Since we decided that the thing we're looking for is to the left of mid, which is 5, right is now 4. So we're down to just one element, element 4. And we compute mid equal to half of left and right. So mid is also equal to 4. And we have a hit, so we're done. We return 4. So what's interesting about this is the fact that there are 3 different stack frames, all for the same 4-parameter bsearch method on the stack at the same time. And so at any one time, we have 3 different variables called left, 3 different variables called right, 3 different variables called mid, 4 different variables called find me, and 4 different variables called I. And so the question is, if I write code that refers to mid or left or right, which one am I accessing? And the answer is always, you can only access the local variables on the top of the stack at any given time. All the other ones are inactive. You cannot access these local variables at all until the methods above them return. Any questions about that? Yeah? Uh-huh. Oh, all right. So there is a mechanism by which one method returns a value to another, which involves the stack, and I'm not sure exactly how it works, but maybe you can visualize it this way. bsearch returns a value, 4, and maybe it just has a special place where it leaves the 4 just written on top of the stack for the next stack frame down to get that value. And then if you go back and look at your code, you'll see that what the next stack frame down does with this value is it just returns it immediately. It doesn't even store it in a local variable. So this bsearch just returns a 4 to this bsearch, and that bsearch, without even storing the 4, just returns it down to the next bsearch, and so on. All these bsearches are just returning the 4 to main, because that's their job. Other questions? All right. One thing that you should know about stack frames is that, unfortunately, while most operating systems have a limited amount of room for stack frames, like, you can probably safely store a few thousand stack frames on the stack, but if you want to store 1 million stack frames on the stack, then it's probably not going to work. And if you want 1 billion, it's definitely not going to work. So typically, most operating systems give you enough stack space for a few thousands or tens of thousands of stack frames. When can this be a problem? Well, so if you're walking through a list using a recursive method, and that list has 10 million items in it, then your program is probably going to crash. Java just isn't up to that. So if you think you're going to want to walk through a list of 10 million list nodes, you probably want to use an iterative algorithm and not a recursive algorithm to do that. On the other hand, if you have an algorithm like binary search, where the number of recursive calls is logarithmic in n, that's always going to be okay, because the log of the total number of subatomic particles in the universe probably isn't more than 300 or so. So if you process the entire universe on your computer, you'll need 300 stack frames to binary search it. So what happens when you run out of stack space? Probably Java will throw a runtime error on you. And then if you have a recursive method for sorting a 1 million element list, you'll probably post something on the CS61B news group saying, "Why is Java crashing?" One last thought about this. Binary search works on arrays, but you can't use it on linked lists. Think about why. So in most programming languages, there's an idea of something called scope, which I just touched on here. Scope is the question of, if I try to address a variable at a certain point of my code, and there are a lot of variables with the same name, which one am I addressing? So, for instance, here, like I said, there's 4 different variables called findMe. If I write code that says findMe equals 2, which findMe did I change? And the answer is generally the one on top of the stack. But of course, there aren't just local variables, there are also fields, and both static and non-static fields. So I want to sort out how all of these get addressed. So first of all, the scope of a variable is the portion of the program, like actual lines of code, that can access the variable. And so here are the scoping rules we've learned so far. Unfortunately, inheritance will make these more complicated, but for now, here's what we know. First of all, let's look at a class variable like number of humans. Remember, class variables mean static fields. These are in scope everywhere in the class except when they are overridden by local variables. Well, let's say shadowed by local variables or parameters, which are really local variables. So you might recall there were places where we had to write things like this dot item equals item, because there was a field called item, and there was also a local parameter called item, and the two were in conflict because they had the same name. So if there's a local variable, the local variable will shadow the class variable so that you can't read it directly. The way to fix that is by using something called a fully qualified class variable. Fully qualified is a fancy name for saying we disambiguate which particular item we're looking in by putting something in front of it. So for instance, when you write system.out, that disambiguates it from all of the other possible outs that you might be referring to. So you might have a million variables called out, but this tells us that we want this particular class variable in the system class. And so these are in scope everywhere in the class, and they cannot be overridden by local variables or anything else. Or shadowed, let's say. Shadowed is a better word. And if they're public, they are in scope everywhere. Number 3 on the list is now we have instance variables, which are pretty much like class variables. In other words, fields that are not static. These are in scope in methods that are not static. Except, again, they can get overridden or shadowed. So this dot item can be shadowed by item as a local parameter. And so that's why we also allow instance names to be fully qualified. And fully qualified instance variables, examples of that are Kayla.name or this.item. When are these in scope? Well, exactly the same as when fully qualified class variables are in scope. Basically, they're always in scope in the class, and if they're public, they're always in scope everywhere. And lastly, we have local variables, which include parameters. And these are only in scope inside the method that defines them. In fact, they're only in scope in the block that defines them, for those of you who know what that means. Like, for instance, if you declare a for loop that says for int I, that I is only in scope inside the for loop. Now, these can't be shadowed. They shadow other things. And, of course, they're only available for the topmost stack frame in recursion.